Thanks for coming. We're gonna get started with this first webinar. This is going to cover energy and work mostly. So let me kind of talk about changes to AP and kind of what's happened in the last few days. So you guys there. We're in weird times right now, as you guys all know. All these webinars that we're doing, we're going to record them. We're going to post them to the A+ College Ready Science YouTube channel. I'll be sending direct links to your teacher so that they have those. These are completely separate than the webinars that the College Board is doing. Your teacher will also have a schedule of those. In a lot of subjects, they actually started with topics that aren't going to be on the exam. I'm not sure why they did that. That's not true for physics, but we'll be in touch about both sets of webinars, the College Boards and the A+ College Readies. If you haven't already, go ahead and mute your microphone and turn off your camera unless you have a question. Feel free to ask questions along the way. If you don't know how to operate Google Hangouts, just kind of click near the bottom of your screen and you'll get a little bar that comes up. You'll see a microphone icon and a camera icon. And if you just click on each one of those, you can turn off your microphone and your camera that way. The PowerPoint that I'm going to be using today, I've already sent out to your teacher. So if you'd like a copy of that PowerPoint, just email your teacher and they can send you one. The next one of these is scheduled for March 31st. It's going to be a 1 o'clock webinar, and you can see the link right here for that one. That'll take you straight to it. Your teacher will be sending out a link to it as well, I'm sure. So this year's AP Physics 1 exam is different than it's ever been before. It's only going to cover units 1 through 8. Normally, there are 10 units in the course. What ended up getting cut out of this year's course is electrostatics and DC circuits, and also waves and sound. There shouldn't be any questions about those topics on this year's test. There are going to be 2 exam dates. We don't know what those dates will be yet. They're supposed to be announced on April 3rd, we hope. The exam is going to be completely online. You can take it at home. You'll need a laptop, a phone, or a tablet. They say any of those should work, or just a desktop as well. The test is going to be completely free response, and it's going to be 45 minutes. So they haven't released any details about what the test is going to look like yet. Typically, there are long free responses and short free responses. My guess is, since they're only going to have 45 minutes, I think they will probably use short free response questions. And my guess is there can't be more than 3 to 4 of those. They're trying to assess the whole curriculum in 3 or 4 questions. So my guess is they're going to be pretty general, and that probably the questions will have to be a little bit easier than they normally are, just because they don't have all those multiple choice questions and they don't have as many free response questions as they normally have. They're supposed to release the details of the test on April 3rd. So as soon as we get those, we'll be talking to your teachers and to you guys about those. So before we get started in the content, does anyone have questions about the exam, how it's going to work, that kind of thing? All right, we're going a little further then. Today's topics are going to be work and energy and power. And the way we're going to try to work on this is we're going to do a quick review of the content. We'll go through a few multiple choice type questions just to review the content. And then we'll end, hopefully today, with a free response question. If we don't get to that free response question, the next webinar will be all free response on this topic, work, energy, and power. So first of all, let's do a little bit of review on our topics. So energy, you've talked about energy your whole life, but in physics, it has a specific definition. It's the ability or capacity for doing work. We talk about different kinds of energy in physics: kinetic, thermal. Not so much in AP Physics 1 with thermal. We just touch on it a bit. Typically, we would talk about electrical, not so much this year. Chemical, not so much this year either. Nuclear is something you might talk about a little bit in AP Physics. We'll also talk about potential energy. You guys hopefully know that we measure energy in joules, which is equivalent to a Newton times a meter. So it's a Newton meter. Types of energy we'll talk about in this course. First of all, mechanical energy. Mechanical energy is the potential energy plus the kinetic energy. You need to make sure you know that definition because they ask a lot about mechanical energy on the AP Physics 1 exam. It is the sum of the potential and the kinetic. It doesn't include thermal or any of those other kinds of energies. It's simply potential, kinetic, the sum of those two together. So you guys know that kinetic energy is the energy an object possesses when it moves. Most of the time, we talk about linear or translational kinetic energy. And the formula for that is 1/2 mass times velocity squared. This formula will be on your AP formula sheet. We're assuming that you'll still be allowed to use that formula sheet. I don't know why you wouldn't. They'll probably just give you a digital copy of it that you can flip back and forth to, I would imagine. Also, though, there's rotational kinetic energy. This is like when a wheel spins. So the formula for rotational kinetic energy is 1/2 I, which is the moment of inertia, times the angular velocity squared. We'll talk a little bit about how both of those can come into play. Like say you have a wheel rolling down a hill. It will have both translational and rotational. We'll talk about an example problem of that. If we don't get to it today, we'll get to that when we get to the free response section. Another thing we talk a lot about in this course is gravitational potential energy. So this is the potential energy that an object has due to its position, usually above the ground or above the earth. Here's our equation for potential energy. Lots of times you'll see books use a P or a PE. Here they use a U. It's mgh or mg delta y, which is the change in height. We also will deal a lot with elastic potential energy. So that's the energy stored in something because of a deformation of something that's elastic, like the stretching or the compressing of a spring. We might also talk about this in terms of a pendulum. But the elastic potential energy is 1/2 K, which is the spring constant, times the displacement squared, or the distance moved squared. So this unit's also a lot about work. So work is when a force acts on an object and it moves a distance parallel to the direction of the force. Work causes changes in kinetic energy. That's a big idea in AP Physics 1. Here's our equation for work. So it's force times distance moved times the cosine of theta. Theta is the angle between the direction of the distance and the direction of the application of the force. So it's the angle between the direction of the force and the direction of the movement. And that angle is going to be important in lots of problems. Work is a scalar, which means that magnitude is really the only important part of work. But this gets a little bit confusing. Work still needs a sign, a positive or negative sign. If work is positive, that's telling you that the force is acting in the same direction as the distance moved. If it's negative, it's telling you that the force is acting in the direction opposite of the motion, opposite of the movement. If you calculate a positive work, think of that as adding energy to the object that's being worked on. And if you do negative work, think of that as removing energy, converting that energy to another form on the object that's being worked on. So remember, work is only done if the force acts in a direction parallel to the motion, either the whole force or it might be just a component of that force. And like energy, work is measured in joules or newtons times meters. So we're going to go through a few practice problems. So what I'd like for you guys to do is take about a minute or two, read through the problem, try to solve it on your own. If you've got some paper beside you, go ahead and try to do what this says. And then I'll go through them and explain them here in just a second. So take about 1 minute, see what you can do here with question number 1. All right, so it seems like on every AP Physics 1 exam, you're asked to draw free body diagrams. So it's important to know how to do one. And I would imagine on this year's exam, there'll probably be a free body diagram more than likely. So with the free body diagram, you're going to show all the forces that act on that object. You're going to show those as arrows. And the length of the arrow should be proportional to the size of the force. Also, the arrow should indicate the direction the force is acting in. So here we have a trash can. I'm just going to draw it as a box. It's sitting on a flat table. We're just going to draw it as a box. There's a force acting on it via a rope, an applied force. It's acting to the right, 50 newtons. So I'm going to go to the center of that box, and I'm going to draw an arrow to the right, and I'm going to label that as FA. That's applied force. So there's also a frictional force of 30 newtons that's acting between the surface and the can. Friction always acts in the opposite direction of motion. So if the box is being pulled to the right, friction is going to act toward the left. Also notice that the frictional force is 30 newtons. The applied force is 50. So when I draw my arrow for frictional force, I need to draw it shorter, proportionally shorter than my arrow for the applied force. So maybe something like that. And I'm going to label that one as F sub F, frictional force. Now, what you can't forget about is there are also some vertical forces acting here that aren't directly talked about in the problem. The box is sitting on a table. It's being pulled on by gravity. So there's a weight force acting on this thing. And the weight of an object is its mass, which in this problem is 4 kilograms, times the acceleration due to gravity, which, remember, on AP Physics, we always use the approximation for G as 10. So the weight of this box would be 4 kilograms times 10 meters per second squared. So that would give us 40 newtons as our gravitational force or our weight. And that's going to act straight down on this box. We're going to draw that arrow a little bit bigger than the frictional arrow and a little bit smaller than the applied force arrow. And I'm going to label that as FG. You could also label it probably as W, weight. Now, a lot of you might stop here and think you've got all the forces covered. But remember, this box is sitting on a table. This can is sitting on a table or a flat surface. So if weight pushes down, the surface has to do something equal and opposite in the upward direction. We call that the normal force. And unless you're on some kind of weird slant or something, typically your weight and your normal force are going to be equal but opposite to each other. So we're going to draw the normal force acting up. And that's a terrible up. That's supposed to be straight up, guys. And that arrow should be the same length as my FG arrow. And I'm going to label that as F of N, the normal force. So I think that's got all of our forces covered. And what I hope you see is that vertically, this normal force arrow and this gravitational force arrow, those cancel out. And that the FA is bigger than the FF. So that means we have a net force acting toward the right, horizontally. Nothing going in the vertical direction. Something else to keep in mind about free body diagrams is that in a lot of problems, you may have to use components of forces to work out the problem. In the free body diagrams, you don't show components. You show the exact force. So don't break a force into components and draw that into your free body diagram. Simply show all the forces. You can still use the components to work your problems, but don't show those on your free body diagrams. Make sure if you have a question, you chime in and let me know. So there's a more artistic looking version of our free body diagram. Now let's look at another question related to that same prompt. So here we have a can. It's pulled across the surface. Same setup. We want to know how much work was done by the applied force. So just this force, the 50 Newton force. Now remember that our work is equal to FD cosine of theta. So in this case, our work is equal to the force, which is 50 newtons, times the distance. Well, the can is pulled the distance of 10 meters, times the cosine of theta. Now, here's what we got to think about. Our box is moving this way, and our force is also this way, which means the angle between our force and our direction, our movement, is 0. The cosine of 0 is 1, which means 50 times 10 times 1 gives us a work of 500 Newton meters or 500 joules. So B would be our correct answer here. Now let's go ahead and look at 3, which again looks like the same problem, but in this case it wants to know how much work was done by the frictional force. So again, same equation. Work equals force times distance times cosine theta. So in this case, we're looking for the work done by the frictional force. Frictional force is 30 newtons. The distance moved is still 10 meters. But the tricky part of this problem is that angle, theta. So here's our box. It's moving this way 10 meters. That's the direction of the distance. But the frictional force is acting this way. So the angle between these two things, the force and the distance, that angle is 180 degrees. And I hope you know that the cosine of 180 is minus 1. So our work is going to be equal to 30 times 10 times minus 1, negative 300 Newton meters, or negative 300 joules. So our answer there ought to be C. Any questions there? All right, so now we're looking at question 4. Again, it looks like the same problem. Here we want to know how much work was done by the gravitational force. So again, we're going to go work equals the force. The gravitational force is the weight, 4 kilograms times 10 meters per second square, 40 newtons. The distance is still 10 meters. But now we got to think about the cosine of the angle. Our box is moving in this direction. Our force is acting in this direction. The angle between those is 90 degrees. So that's cosine 90. The cosine of 90 is 0, which means our work is 40 times 10 times 0. Our gravitational force does 0 work because there's no part of that force that acts in the same direction as the motion. So answer D would be right here. Again, here's question 5. Looks like sort of the same question. We're looking here for the work done by the normal force. So work is equal to force. Normal force is equal but opposite to the weight. So it's 40 newtons. The distance is still 10 meters. Now we're looking at the angle between our force and our direction. So there's our direction. Our force is acting this way. That angle's still 90 degrees. Cosine of 90 is 0. So our work is 40 times 10 times 0. The normal force also does 0 work because there's no component of that force that acts in the same direction as the displacement or the distance moved. All right, so now we get to something that might be a little bit more important for AP Physics 1. Here we want to know how much net work was done. Vertically, we know there was no net work because we had no work in either direction vertically. Horizontally, we had 500 Newton meters done to the right. That was done by the applied force. And we had 300 Newton meters done by the frictional force. And that was in this direction. Well, if we combine those together, the 500 plus the negative 300, because that was to the left, we ended up with 200 joules, positive 200 joules of net work. There you go. So now we got another idea here. If you assume that the initial speed of the can was 0, what's its speed after traveling the 10 meters described above? This sounds like a really tricky problem, but this really goes back to the idea of the work energy equation. And here's what you ought to know is that net work causes a change in kinetic energy, or the net work is equal to the change in kinetic energy. That's a really important idea in AP Physics 1. So we know that the net work was 200 Newton meters, or 200 joules. And we know that kinetic energy is 1/2 mv squared. Now here, the change doesn't matter that much because we're starting with 0 kinetic energy. So our final kinetic energy is going to be equal to 1/2 mv squared. And that's the change in energy because we started at 0. But do note that if you don't start at an initial speed of 0, that you need to calculate the change in kinetic energy, not just the final kinetic energy. In this case, since we started at 0, we're going to calculate our final amount of kinetic energy. Notice we've set our work equal to the equation for kinetic energy. So 200 Newton meters is equal to 1/2 mv squared. Here we know the mass. We know the mass is 4 kilograms, and we can solve for velocity. So I'm going to go ahead and go 1/2 times 2 and get 2. I'm going to divide both sides by 2 kilograms. So I'm going to end up with 100, and I'm going to come up here to the top where I have a little space, Newton meters per kilogram equal to V squared. Now let's talk about the units for a second. I hope you guys know that a Newton is a kilogram times a meter per second square. In this case, we're also multiplying that Newton by an additional meter, and then we're dividing it by a kilogram. So you should see that the kilograms here are going to cancel out, and that the unit we're left with is meters square over second square. So right now we have 100 meters square over second square equal to V square. So let's take the square root of both sides of that, and we end up with a positive 10 meters per second when we take the square root of both sides. So there we go. Now, notice they're not very picky about significant digits on the AP Physics 1 exam. But what I would look at is if all of your initial numbers have 3 significant digits, I would make sure that I gave an answer with 3 significant digits. If some of your initial numbers in your problem only had 2 significant digits and others had 3, I would give my answer to 2 significant digits. Always round it to the least number of significant digits that you were given in your problem. Any questions so far? All right, so another important idea that we'll talk just briefly about in this unit is power. So power is the rate of doing work, or how fast is work done. You can also think about it as the amount of energy that's transferred from one place to another per unit of time. It doesn't have a direction, so power is a scalar. In the SI system, or the metric system, the unit of power is a joule per second, and we call that unit the watt, joule per second. So there's several ways to calculate power. On your physics formula sheet, your AP Physics 1, you may see it written this way. It's a change in energy per unit of time. Oftentimes we'll write it as work per unit of time. Remember that work is force times distance. So you could substitute FD for W. And something that they might throw at you that's a bit tricky is that if we have power is FD over T like this, remember that distance over time is speed. So you could also write it as power equals force times speed. And occasionally they might throw a problem at you where you have to derive that equation and know that power is force times speed. So just be aware that that could happen. In this year's situation, we don't really know what they might throw at you. But be able to derive all 4 versions of this power equation. Something else we'll mention briefly here, talk about conservative versus non-conservative forces. So I'm just going to, in this case, read the definition to you. So a conservative force is a force that converts potential energy to other forms of mechanical energy. Typically, that's going to be kinetic, or maybe another form of potential energy. A conservative force conserves mechanical energy as it does work. So the work done by a conservative force is path independent. Doesn't matter if the object moves in a path like this, or if it moves in a path like that. The change in energy is still going to be the same. The only thing that matters when we're talking about conservative forces are the initial and final positions of the object. The major conservative forces that you're going to work with in AP Physics 1 are either gravity or the force that's in a spring or in some kind of elastic object. On the other hand, let's contrast conservative forces with non-conservative ones. So this is a force that can change the amount of mechanical energy in a system. And typically what that means is when this force is acting on the object, some of that energy is converted to a non-mechanical form of energy, like heat, like sound, maybe even light. So the work done by a non-conservative force is dependent upon the path. That's important. The major non-conservative forces we're going to work with in this course are friction and drag, mostly friction. So if you see friction in a problem, realize that it's a non-conservative force and it can change the amount of mechanical energy, potential and kinetic energy in your system. We already talked a bit about the work-energy theorem a minute ago. It's the idea that the net work done on an object is equal to the change in the kinetic energy of that object. Think of that as what happens when we're doing, well, we can think of it this way for conservative forces. So we can think of the final potential energy minus the initial kinetic energy is equal to the work. When we're dealing with non-conservative forces, we also might think of it this way. Change in kinetic plus change in potential is equal to the amount of work done. Like I said a minute ago, realize that the kinetic energy term in the equation can be for both translational or linear and rotational kinetic energies. So for example, if you had an inclined plane and you had a box up here, and you also had some kind of like rolling object, like a wheel, and you let them both roll down that plane at the same time, you might be asked a question, which one makes it to the bottom faster? Or which one is moving fastest when it gets to the bottom? Well, if you let them both go at the same time, and you assume the friction acting on both is the same, the box is going to make it there first. And the reason the box is going to make it there first, and let's just say in this case, there's no friction. That'll make this an easier thought. If there's no friction, that means all the potential energy of this box is converted to kinetic energy. And since the box doesn't roll, it doesn't spin, all of the potential energy is converted to translational or linear kinetic energy. So that gets it to the bottom fast. With this rolling object, two things happen as it's rolling. One, some of the potential energy is converted to translational, linear movement, linear kinetic energy. But some of it is also used to cause that wheel to spin, and it gets built up in terms of rotational kinetic energy. So this thing is spinning and moving translationally. Therefore, at least linearly, it's moving slower than the box. And again, that's because all the potential energy in the box is converted to translational kinetic energy. Whereas with something rolling, some of that potential energy is converted to rotational kinetic. Other parts are converted to translational kinetic. They like to throw those kinds of problems at you. Just make sure you understand why that's the case. Any questions here? All right, another thing they like to throw at you are graphs. And I'm sure they'll throw some kind of graph at you on the exam. Whether you'll have to actually draw a graph or interpret a graph, we don't really know yet. Hopefully we'll know more about that in the days to come. This wants to know what is the change in the box's kinetic energy between 0 and 4 meters. So notice this is a force versus position, or we could think of it as a force versus distance graph. What you want to think about here, when you're finding the area under a curve, which is what we're going to do here. So we want to find the area under this curve. When you're finding an area, essentially what you're doing is you're multiplying whatever's on the y-axis, which is in this case is force, times whatever's on the x-axis, which in this case is distance or position. Remember that force times distance is work. So when you have a force position graph and you find the area under the curve, you're essentially finding work. So let's find the area under the curve. So between 0 and 4 meters. Easiest way to do that is divide this into two chunks. Let's first go from 0 to 2 meters and find this area, the area right in here. So essentially we're going to think of this as a rectangle. The rectangle has a height of 40 newtons and it has a width of 2 meters. So we're going to go 40 newtons times 2 meters, and we're going to get 80 newton meters, positive 80 newton meters for the area under that first part. Now we want to find the area under the second part of the graph, which is from 2 to 4. Remember, the problem only asks us to go to 4 meters. So we're going to essentially make this a rectangle from here to here, between 2 and 4. So this rectangle has a height of -20, and it has a width of between 2 and 4, so of 2. So we're going to go -20 times 2, and we're going to get a work here of -40 newton meters. Now we want to add the two areas. So add the area from the first box to the area of the second box. So 80 plus -40, we end up with positive 40 newton meters of work, or positive 40 newton meters of change in kinetic energy. Remember that work is equal to change in kinetic energy. And think of this as net work is equal to change in kinetic energy. So they will very oftentimes throw a force position graph at you. Remember, if you're finding the area under the curve, you're multiplying y times x. Now, there are other cases where you might need to find the slope of a curve. When you're finding the slope, you're essentially taking your y and dividing it by your x. So in this case, it would be force over position, or force or newtons over meters in this particular problem. All right, so here's another problem. This one has to do with, again, the work energy idea. So here we have a bike rider and his bike. They have a combined mass of 90 kilograms. Instead of a bike, it might be better to think of this as almost like a guy on a board that's sliding down a hill. Let's think of it. Let's take out the bike, because we don't want to have to think about the spinning of the wheels. So the rider starts from rest and rolls down an incline plane. So I'm just going to think of this guy as a box. So he starts with a speed of 0. His initial speed is 0. And let's just think if he's sliding instead of rolling down the incline plane a distance of 500 meters. So the plane is inclined at 5 degrees above the horizontal. So this angle, 5 degrees. The average frictional force acting on the bike is 60 newtons. Find the speed of the bike at the bottom. So here's the deal. We need to know how much net force is acting on this guy. We know we have 60 newtons of frictional force acting up the plane. But we also know there has to be a force pushing the guy down the plane. And the easiest way to do that is to go to the center of the box, draw in the weight. We know weight acts straight down. So let's draw in the weight. The weight of this guy is going to be 90 kilograms times g, times 10 meters per second square. So this is going to be 900 900 newtons is the guy's weight. We need to resolve this weight into components. We need to resolve it into a component that's perpendicular to the plane, like so, and a component that's parallel to the plane, like so. We're going to call this the parallel component, and we're going to call this one up here the perpendicular component. When you do this kind of vector resolution on an incline, the angle of your incline is going to be equal to this angle right here, the angle between the angle up here at the top of your triangle. So this is 5 degrees. We know the weight is 900. What we really need to know is the parallel component of that weight, this side of the triangle. So to do that, we could use the sine function. And we could say the sine of 5 degrees is equal to the opposite side. Opposite of this angle is going to be this side right here. So the parallel component over our hypotenuse, which is our weight, that's this side, 900 newtons. So I'm going to go to the next slide where I've already calculated this out. So what we end up with, let me go back here for a second, guys. So let's just look at it this way, since I've already got it worked out this way. So here, we're going to use the sine function. We can find the height. There's 2 different ways we can work these problems. We could have worked it the way that I was approaching it there by finding the forces. But let's show you the easier way to do this, and let's do it in terms of energy. So if we go back to our problem, our plane was 500 meters long. So this distance is 500 meters. This angle is 5 degrees. So we can find the height of the incline. And to do that, we would go the sine of 5 degrees is equal to the opposite side, h, over the hypotenuse of 500. Solve that out, and we end up with h of 43.6 meters. Well, now that we've got the height, we can calculate the initial gravitational potential energy of that rider, of that guy. To do that, potential energy, gravitational potential energy is mgh. So in this case, the guy's mass was 90 kilograms. We know that g is 10, and our height, 43.6 meters. Calculate out that gravitational potential energy. You end up with 38,494 joules. Now we can also calculate the work done by friction. The work done by friction is the force of friction. And in this case, the force of friction was 60 newtons. The distance that the box slides is 500 meters times the cosine of the angle between the distance moved and the frictional force. And those are going, if we got our box up here like so, the box is moving this way, friction's acting that way, so the angle between those two is 180 degrees. So when we calculate this out, we end up with a work done by friction of negative 30,000 joules. There's negative 30,000 Newton meters. Well, here's the deal. When there's no friction, which is what this problem would say, if there was no friction, all of the potential energy that we started with, all 38,494 joules, would be converted to kinetic energy at the bottom of the plane. With friction, though, 30,000 joules of that gets canceled out. It gets converted to heat. So what's left, 30,000 joules is wasted, is turned to heat. What's left is 8,494 joules. that 8,494 joules is equal to the net work. We know that net work causes a change in kinetic energy. So let me make a little space here. So we've got net work equals change in kinetic energy. So our net work is 8,494 joules, and that's equal to our change in kinetic energy, which, remember, we started at 0, so we can just calculate our final kinetic energy since we started at 0. Let's do a little bit more math here. So 1/2 times our mass, and in this problem our mass was 90 kilograms, times v squared. So essentially we're going to divide both sides by 45 kilograms, and then we're going to take the square root of both sides, and we're going to end up with a final speed of this guy at the bottom of the hill of 13.7 meters per second. So I can see them throwing a problem like that at you. I'm going to show you one other type of problem, and then we'll go from there. So a box slides down a frictionless inclined plane at 10 meters, of length 10 meters. The plane is inclined at an angle of 20 degrees above the ground. If the box starts from rest, what is its speed at the bottom of the plane? So again, this looks a lot like the problem we started with a minute ago. But here's the deal. So first of all, we're going to use the sine function to find the height of the box, just like we did in the last problem. So the length of our plane is 10 meters. So this side is 10 meters. The angle is 20 degrees above the ground. So let's first of all find the height. So we're going to say sine of 20 equals opposite, which is going to be h over the hypotenuse of 10. So when we do the work on that, our height is going to be 3.42 meters. Well, we can use that height and the mass to find potential energy. But in this case, if we go back to the problem, we don't know the mass. So that becomes a bit tricky. What we do know, though, is that the plane is frictionless, which means that all the potential energy that we started with up here should be kinetic energy by the time we get down here. So let's write it something like this. I'm going to write that as initial gravitational potential energy should equal to final kinetic energy. But since we don't know the mass, at first, this might seem a bit confusing. But here's where we've got to be a little bit tricky, and I can see them putting this kind of problem on the exam for you. Remember that gravitational potential energy is mgh. Also remember that kinetic energy is 1/2 mv squared. And what I hope you see is that the mass is the same on both sides of this equation. That means the masses cancel out. You don't need to know the masses. And you end up with GH equals 1/2 v squared. Well, we're trying to solve for the final speed. So let's solve this out for v. We need to get rid of the 1/2 by multiplying both sides by 2. So we end up with 2GH equals v squared. And then we need to take the square root of both sides. We know G is 10. We found H is 3.42. So when we solve this out for V, we end up with a final speed of the box at the bottom of the hill of 8.19 meters per second. All right, the last couple of things I'll talk about, we'll try to end this here in about 5 minutes or so. The total energy of a system is always conserved. It's the law of conservation of energy, the first law of thermodynamics. That's even when acceleration is not constant. Now, in cases like that, where the acceleration isn't constant, you can't use the kinematic equations. Those kinematic equations like VF equals VO plus AT, those only work with uniform acceleration, constant acceleration. But the laws of mechanical energy or conservation of mechanical energy, they can still work. They always work. One other thing that you want to remember, though, is that difference between mechanical energy and total energy. If friction or drag are involved in a problem, even though the total amount of energy in the system is conserved, the total amount of mechanical energy is not. Because remember that mechanical energy is your potential plus your kinetic. When you have friction and drag involved, you also bring in that extra variable of heat or thermal energy. So some of the mechanical energy, when friction or drag are involved, are converted to thermal energy. All right, I want us to just preview the FRQ we're going to start with next time. Our next session will be all FRQs, and it'll be all FRQs related to either work or energy or power. This is the first FRQ we're going to deal with. This is from the 2015 exam, and it's a spring kind of system. It looks at first like it might be a simple harmonic motion problem, but it isn't. So between now and next time, I'd like for you guys to look at this problem and try to figure it out. If you don't have a copy of the PowerPoint, if you'll just Google 2015 AP Physics 1 free response questions, you'll be able to find it. It'll be an easy find. But this one involves some graphing. It involves some qualitative answers. So if they ask you for a qualitative explanation, they want you to explain things in terms of words. No equations, no math, just words. But later on in this problem, they also want you to do some quantitative reasoning. They ask for quantitative reasoning. They want you to use math, use equations, use math, explain things in terms of mathematics. And we'll see both parts of that on this particular session. I don't think we have time to start working into this problem today. So I'm going to stop there, and I'm going to take a minute to ask any or answer any questions you might have, and we'll go from there. So does anyone have questions that I can answer for you?
Okay, yes. When are you supposed to use 9.8? It's like the 9.8, like I think you used it in the last problem. Did you use
Yeah,
like
so in physics 1, you always want to use 10. The acceleration due to gravity is actually like 9.81 meters per second square. But to make the math easier in AP Physics 1, you want to always use 10.
Okay.
So don't whether we're talking about multiple choice or FRQs, always use 10 for G. Other questions I can answer for you guys? All right, well, we're going to stop there. Thank you guys for participating. I'll upload this to YouTube, and I will send a link out to your teachers. Thank you. Please.